Okay, hello and welcome to another amazing lesson. Today we're covering lesson 2 of Unit 5, Rational Expressions. And today we're going to be investigating reducing rational expressions. We're going to start off with equivalent fractions just to help you remember using maybe a grade 10 analogy. So you can write an equivalent form of a rational number by multiplying or dividing the numerator and denominator by the same value. Functions very similar to how you might multiply 2/3 by 3 on the top and the bottom to get an equivalent fraction. So let's take a look. If you take 2/3 and you multiply by 3/3, that's really just a form of 1, so you're not really changing it. So 2 times 3 is 6, 3 times 3 is 9, and now we know that 2/3 is the same thing as 6/9. Easy enough. You can do the same thing with division. So if there's a common or a greatest common factor in a fraction, so if you have 12 over 15, you can divide the top and the bottom by the same factor, and you will get 4 out of 5, which is also an equivalent form of 12 over 15. Usually we wish to reduce the smallest equivalent fraction. This is especially important with polynomials. Being just generally more complicated, we always want to reduce them. All right, so equivalent expressions. Like I was saying, we can do exactly the same thing with rational expressions. Here's a messy looking rational expression. Okay, so we got 20xy over 8x squared. We can say multiply by a form of 1. So in this case, we're multiplying by x over x, which does divide out to just 1. And an equivalent form of this initial beginning fraction, rational expression rather, is 20x squared y over 8x to the 3. Notice the non-permissible value. That's what we were doing yesterday. Or likewise, we can reduce it. So in the top example, we've made it more complicated. In the bottom example, I'm noticing, hey, well, 20 and 8 are both divisible by 2. So I'm going to divide by 2. And there's an x in the numerator and 2 x's in the bottom, right? There's x squared, so that means that there's x times x. So there's 2 x's down there. So I'm going to divide the top and the bottom by 2x. 20 divided by 2 is 10. X divided by x is 1, so we're just left with the y. So you can see we got 10y in the denominator. 8 divided by 2 is 4. X squared divided by x is x. And you still keep your non-permissible value. By the way, the non-permissible value, you are always going to grab that from the initial rational expression. So it's going to come from this initial rational expression, not the reduced one. So we'll talk about that later, but just thought I'd mention it now. All right, so all these things are equivalent expressions. And generally, we want the one that's the most reduced, so that's the one we would go with. All right, next slide, our first example. So this one, we're not actually, it just says we're going to use multiplication and division to write an equivalent form of this rational expression. So really, there's two things that can happen here. If we use division, we can divide out any common factors. So an x plus 2 in the numerator and an x plus 2 in the denominator are the same thing, right? It's like having the same number. So we can actually divide these out, and that would divide out to 1. So one equivalent form of this, which is completely reduced, would be 3 over x minus 4. We should always write our non-permissible value. So if I go back to the original one, x cannot equal -2 and 4. So -2 is not okay and 4 is not okay, right? So you'll notice that if you look at the reduced one, it no longer appears that x equal -2 is a non-permissible value, but we always look at the original function. An equivalent form using multiplication. So for this one, I'm just going to recopy it for a second. I could just arbitrarily multiply it by, say, I don't know. Let's go with something crazy like y over y. All right, so I'm going to do that in a different color. So if I multiply by y in the top and in the bottom, in the denominator there, this would be an equivalent form. And our non-permissible values are still x can't equal -2 and 4. And also, because I introduced a new variable here, y couldn't be 0. All right, next example. Your turn, very similar. Not too worried about that. All right, a rational number is in simplest form when the numerator and denominator have no common factors other than 1. right? So if you look at 2/3, there is no 2 and 3. Their greatest common factor is 1. All right, so that's how I know it's in lowest terms. A rational expression is also in lowest terms when the numerator and denominator have no common factors other than 1. So exactly the same as a fraction. If you have a rational expression, so something like this, if the GCF is 1, it's in lowest terms. So 2x minus 1 and x minus 1, their greatest common factor is 1. All right, important. Very important. When two rational expressions are equal, they are equal for all the values of the variable for which both expressions are defined, including the non-permissible values. Okay? Right on. Oh boy. So rules for canceling rational expressions. So you can only cancel like terms. For example, comma, you can cancel a monomial with a monomial, a binomial with a binomial, or a trinomial with a trinomial, as long as they are alike. This is one of my favorite phrases. Don't be cancel crazy. You can't cancel pieces of a binomial or a trinomial. So what I mean is, if you look at this example here, this is a monomial. In the denominator, we have a binomial. You cannot just go x divided by x is 1 and write this as 1 over 6. Those are not the same thing. Okay, so you cannot cancel a monomial with a binomial. These are two different numbers. Okay, let me demonstrate. If x is 7, for example, then I would have the expression 7 over 7 plus 6, 13. Okay, if you just cancel the x's, it's no longer the same. Okay, so this is also very important. I would put this down on a piece of paper on your cheat sheet for the unit. Sometimes we do something called a reversal. Okay, so that just means that we're basically going to be pulling out a negative in order to make something look a little different. So at first glance, if you look at this expression here, 1 minus x divided by x minus 1, you might think, that's not the same thing. Like, can't do anything there. In reality, you can. You can simplify it further. If you factor out a negative 1 from the numerator, you can actually do some canceling. So factoring out a negative 1 from the numerator would mean changing the signs in the numerator. So down here, I factor out my negative 1, and I divide each term by negative 1. So my positive 1 becomes negative 1. My negative x becomes positive x, right? If I distribute this into the brackets, I need to get back to where I started, to 1 minus x. Okay, and that's the case. Now that you've done that, negative 1 plus x, you can rewrite, right? You can just switch the order here, and you can write x minus 1. All right, so now all of a sudden, I got my negative 1 out here in front, but x minus 1 and x minus 1 are both binomials that we can cancel out to 1. All right, so then we would have negative 1 times 1, or 1 in the numerator, and in the bottom we have 1. So overall, this expression equals negative 1. Okay, so that's some mathemagics for you. So if you ever see something that in general looks like a minus b divided by b minus a, so the two terms in the denominator flipped, you know that it equals negative 1. Okay, and that's called a reversal. This is a very important trick. Okay, very important trick. Put it in your back pocket. All right, we're on to example 3. So we're going to just be doing a bunch of simplifications now. Okay, so this one, it's one big term in the numerator and in the denominator, so it's a monomial. It's everything's being multiplied together. I would take it sort of one step at a time. So, let's look at the numbers. So 15 and 20, well, those are both divisible by 5. Okay, so I'm going to do it one step at a time, and I'm going to say, okay, I'm going to divide by 5 on the top and on the bottom. So 15 divided by 5 is 3. I'm going to recopy, then I got x squared y z to the 3. 20 divided by 5 is 4, and then I get x, y, z. Let's see if we can go a little bit faster now. So y divided by y is 1. So I'm going to go ahead and cancel that out to 1. If you have a z to the 3 in the top and a z in the bottom, this z will cancel, and then you can just reduce the exponent by 1. So you have a z squared. Same thing with the x squared divided by x. So x will cancel the squared, and you just have x to the 1. So final answer, you get 3x, and then I got z squared in the numerator and just 4 in the bottom, in the denominator. Okay, for non-permissible values, we got to go back to the original expressions. I'm just reminding you up here, so don't forget to list the non-permissible values for the original expression. So x, y, and z could not be 0. I don't know if the mic picked that up, but something just fell. All right. There we go. Another one. Now this one, sometimes you have to factor in order to see if you can cancel anything. So sometimes we need to factor in order to see what cancels. So let's take a look. I don't see anything in the bottom that I can pull out, but in the numerator, 3 and 8, their greatest common factor is 1, but x squared and x, I can pull out an x. So in the numerator, I'm going to pull out an x, and I'm going to get 3x minus 8. In the denominator, I suppose I'm going to kind of write it like this. I'm going to pull out an x, so to speak. So I'm going to throw it out in front. I know it's a little strange, but now I got x multiplying this and x multiplying this in the bottom, so I can cancel those out to 1. And my final expression is going to be 3x minus 8 divided by 2. Non-permissible values go back to the original expression. I'm seeing that in this one, 2x can't equal 0, right? So x cannot equal 0. That would give me a bad denominator, and we are done. Do not go cancel crazy here. You can't just go put the 2 into the 8 because this is a binomial. Okay, so you'd have to divide both terms. So we're done. Okay. Next. This one looks interesting. So, yes, very sneaky here. I see what's going on. So in the denominator, I'm seeing a difference of squares. So that's going to factor out to x minus 2, x plus 2. And I'm thinking, well, the numerator, it's 2 minus x. When the variable is not first, you probably want to do one of our famous reversals. Okay, so we're going to reverse by pulling out a -1. So if I write a -1 and open a bracket, flip the signs here. So 2 becomes -2. Negative x here becomes positive x. Can I just double check? If I distribute this back into the brackets, you're going to get positive 2 minus x, just like how I started. And then I'm just going to switch the order of these two things, right? So I can write positive x subtract 2. That would be the same thing. So I'm going to write positive x subtract 2, like that, and voila, all of a sudden, I see the light. I have the same binomial. I have x minus 2 divided by x minus 2. So this, I can cancel out to 1. My final expression is -1 over x plus 2, and I'm done. Except for my non-permissible values, which I want to grab from the original expression. So I factored this so I could clearly see the pieces, and I can see that x could not equal plus or minus 2, like that. We are done. Wonderful. Next, this one's got a lot going on. So in the denominator, we're likely looking at doing a decomposition, and in the numerator, we're looking at doing a reversal. Anytime you see that your variable, like I said, is second, you're going to want to do a reversal. So let's do all of that at once over here. So I'm going to pull out the -1 and reverse the order, change the signs on these. So I'm going to get -16 plus x squared. Okay, close my bracket. In the denominator, I'm going to have to do some work. So let's see, I'm looking for two numbers that multiply to 2 times 12, so 24. And those same two numbers need to add to -11. So let's see. My factors could be 1 and 24, nope. 2 and 12, nope. 3 and 8. 3 and 8 look promising. I need them to add to -11, so I'm going to throw negatives on both. So when I multiply them, they're positive. That's looking good. So down here, I'm going to start my decomposition using my two factors. So here we go. So I'm going to write -8x minus 3x plus 12. All right, there it is. So just double check, make sure that these two things actually add up to that. They do. So from the first two terms, I'm going to pull out a 2x. I'm going to pop it in there as one of my outside factors, and I'm going to divide this, and I'm going to get x minus 4 So there's the decomposition. From the second two terms, I can pull out a -3. And when I pull out that -3, I'm going to double check. Do I get x minus 4? So -3x divided by -3 is x. Okay, sorry, we're back. I got cut off there. So yes, -3 goes into -3x and you get x out. And 12 divided by -3 is -4. So we're done. That's been factored. So I'm going to go ahead and copy that over here. There we go. Now, up here, I pulled out the -1. I'm going to go ahead and change the order of these. So I'm going to write positive x squared minus 16. So x squared minus 16. And we know that this factors out. It's a difference of squares. So I'm going to go ahead and do that as well. So I'm going to erase this. And I'm going to write x minus 4 and x plus 4. Like that. Now I can see that there are a few things that cancel. And by a few things, I mean one thing. X minus 4 divided by x minus 4 would be 1. So I can cancel those out. And I can now write my final answer. I'm going to throw the negative in front of the fraction. And I'm going to get x plus 4. That's all I have left in the numerator. In the denominator, I have 2x minus 3, comma, my non-permissible values. So I'm going to be looking at this factored form here before I canceled anything. So one of them is going to be positive 4 coming from this binomial here. And then when I solve 2x minus 3 equal to 0, I'm going to get 3 over 2. And there you have it. Next question. So these are some check your understandings. So basically, this was the first question type that we tried, where it's just giant monomials. Yeah, I think we're okay to skip it. This is the second question type that we did. Very similar, so you're pulling something out from the numerator. And in this case, yeah, I'm going to leave that one. Same thing with this. You can factor it. And this one. And yeah, okay. So that would basically bring us towards the end of the notes. I am going to maybe do a couple of these, so sorry for the mad page flipping. Sure, let's start here. So in this one, in the numerator, between 6 and 12, I can pull out a 6. And between x squared and x, I can pull out an x. So that's going to leave me with x plus 2. Always remember to double check. So if you redistribute this into the brackets, so 6x times x is 6x squared, 6x times 2 is 12x, so everything's looking fine there. And in the bottom, I'm going to write my 3x again. Okay, so this is a monomial, that's a monomial, everything's being multiplied, so I can do some canceling here. So x divided by x is 1, and 3 goes into 6 twice. So now I have 2 times 1 times this, and I can go ahead and write 2 times x plus 2, and you could leave your answer like this, or you might choose to distribute it into the brackets and write it like that. It's all good. Just don't forget your non-permissible values. So go back to the original, and I can see that x cannot equal 0, and I'm done. This one here is going to be just a bunch of factoring. So in the numerator, I have a difference of squares. So I'm going to have x minus 7 and x plus 7. In the denominator, I just have a regular a equals 1 factoring type question. So I'm going to start by writing my x's out, and I'm looking for two numbers that multiply to -14, but add up to -5. So I think it's going to be -7 and +2. There we have it. See what cancels here. So I can cancel these two binomials that are the same. Well, it cancels out to 1. And I can copy my final answer, x plus 7 in the numerator, x plus 2 in the denominator, and I'm going to write my non-permissible values here as +7 and -2. So there's that one. And here's another one, which involves two things, a decomposition in the numerator and a reversal in the denominator. Okay, so again, anytime that you see your variable coming not first, like the x squared, usually we're used to seeing it as x squared, plus x plus a constant term kind of thing, it's probably going to be a reversal. All right, so I'll do the reversal first. Hopefully we're getting a little bit faster at these. So I'm pulling out the -1, which is flipping the signs. So here we are. So now I have this. All right. And then you can change the order of this as long as you take the signs with you, right? So going -9 plus x squared or going x squared subtract 9, that's the same thing. And that's what we're after, is to rewrite that order. Okay. So I'm going to write x squared minus 9. And now I have something that I can factor. It's a difference of squares. Okay, so I'm going to keep the -1 here. You cannot lose the -1, right? Like if I redistribute that into the brackets, I'll get -x squared plus 9, which is this. Okay, so I'm going to factor this one out, difference of squares. So x plus 3 and x minus 3. All right. And in the numerator, I got, my my decomposition. So in this case, I'm looking for two numbers that multiply to 2 times -3, so -6, and add up to -5. And we've seen this one plenty. Those two factors are going to be 3 and 2. And for it to add up to, oh no, they're not. It's not going to be 3 and 2. It's going to be 1 and 6. My bad, because I need it to add up to -5. So it's going to be -6 and +1. So that way it multiplies out to the correct number. So I'm going to recopy my original trinomial using my two terms. So -6 plus 1x minus 3. And I'm going to go ahead and jump straight to the factored form here. Right, so I'm going to double check first. These two things should add up to -5x, which they do, so I'm looking good. From the first two terms, I can pull out a 2x. When I do that, I'm going to get 2x squared divided by 2x, which is x, -6x divided by 2x, which is -3. In the second two factors here, it looks like I can pull out nothing. So that's a lie. I can pull out +1, so to speak. And when I do that, I'll get x minus 3. So I've successfully factored it. I'm going to just kind of put it over here in this last step, just because I'm being lazy and I don't want to write. So there we go. There it is, all factored up. And it appears that I can cancel. I got an x minus 3 and an x minus 3 binomials in the top and bottom. That factors out to 1. So in the numerator, I have 2x plus 1. The negative, we'll just generally throw it in front. So that's a good place to put it, is right in front of the fraction. So I have my negative there. That comes from the -1 here. And then I have x plus 3. Comma, do not forget your non-permissible values. You must always write them. Whether or not it's stated for you to do so, you should always do it. So looking back at my original question, once I factored it, then I can see what the non-permissible values are. So I see that it's plus or minus 3. There we go. Another question done. Okay, couple things just to review before we get to the practice questions. So why can't we reduce x plus 7 divided by x plus 1 to 7 over 1? But we can if we have 7x divided by x. Well, in a nutshell, like we were talking about, we can't just get rid of the x's here and say, oh, it divides out to 1, because these are binomials. Okay, so you can't cancel one piece of a binomial with another piece of something else. It's not equivalent. It's not the same thing. Whereas down here, because these are both monomials, we can go x divided by x and get 1, and 7 times 1 is 7. Okay, so that's basically the gist of that one. For number 14, create a rational expression that has each set of non-permissible values. Explain how you created each expression. Okay, this is fascinating. So you want to make up a rational expression that the non-permissible value would be x does not equal 0. And x cannot equal 6. So, well, if that's the case, remember, when you solve these, you would have had these equal to 0. So you would have, oh boy, what am I trying to say here? Well, you gotta go backwards. Let's start with the x equals 6. So if x can't equal 6, that means that my binomial would have been x minus 6, right? Because when you set x minus 6 equal to 0, you get that x equals 6. So that must have been one of my binomials. If I had an x equals 0, that means that I must have just had an x somewhere in my original rational expression. So, a really easy way to do this would be, well, here it is. There. So this x here, when I use the zero product property, that gives me x can't equal 0. The x minus 6 binomial gives me that x cannot equal 6. So that's the easiest way I can think of to do that one. I could have just put some random garbage in the numerator, but I just chose to put a 1. Like I could have put like x plus 1. If you are going to do something like that, make sure that it doesn't cancel something in the denominator. Actually, no, I misspoke there. It could cancel something in the denominator. It doesn't matter. So here's another one. So if you have x can't equal 4, that means if you go backwards, one of your binomials would have been x minus 4 from that one. And if x can't equal -7, then x plus 7 would have had to have been another one of your original binomials. So I'm going to just be a little fancy for this one. I'm going to write x plus 1 in my numerator for no reason, just because I can. There. So this would have the appropriate non-permissible values. All right. That's a happy day, everybody. We got to the end of the notes. You can check out exercise 31 in your books. Remember, those are very focused and specific practice questions for you to try. Try them out, and I'll see you next time.